Let's see. We have increment submatrices by 1, medium. Haven't done this one. You're given a positive integer n, indicating that you initially have n by n 0 index integer matrix mat filled with zeros. Could have said this was a square matrix given those dimensions. Okay. You're given a 2D integer array query where query at I is going to be 4 values, row column, row column. You should do the following operation. Add 1 to every element in the submatrix with the top corner. Okay, from basically the first 2 are the row column of the first top left corner. The second 2 are values for the bottom right corner. That is add 1 to all values in that area. So here, 3 by 3, all zeros. Make this section all ones, incrementing it from 0 to 1, and then make this section increment by 1, so this makes it 2. And those are the 2 queries, and you return the array afterwards. Okay. Simple enough to understand. I guess I'll just make a matrix. This can be 0 times n for every column. Okay. Okay, very elegant kind of, or simple type of problem. Is there a point in sorting the queries? Maybe sorting the queries makes some sense. Obviously you don't want to manually do it for every query, the actual incrementing of the values. Say obviously, but maybe you can. 10 to the 4th queries, where each query is a 3 by 3, or up to a 3 by 3 if n is 3. Yeah, that's probably not feasible. If each query was, let's say, 500 by 500, let's do some math here. That'd be 2,500 increments of positions. And then if you multiply that by 10 to the 4th, second, third, fourth, yeah, that's too much. It's billions. 2.5 billion. So you can't do the kind of brute force incrementation of every value in every cell of every query. Do you need to track? So the number of queries is 10 to the 4th. Could you track for every cell the queries that are? No, it's probably not doable. So 1122. What if I did a slight collapse? So 1, 1, 2, 2. What if I said that for the rows that are 1 and 2, that I am going to increment the columns that are 1 to 2. And then I do that for each row, keep a track of the intervals that are increasing for that row. Where the intervals are the column, the min column, the min and max column of the increasing spots. And then I do it for per row. That's pretty reasonable sounding. So for each row, keep a list of kind of call 1, call 2, where values in those columns inclusive in that range of columns, calls 1 less than x less than, well, 1 less than x less than column 2 will be incremented. For each query, translate that query to a tuple for the relevant range, relevant rows. Okay, so there'll be rows, row query or row increments. Row increments, sure. So this is going to be an empty list for each column. For each row increments. Should these be called row increments or column increments? I guess this should be, I'll just call it increments. For each in the range of rows, where rows and columns, I should probably make this capital caps because it's constant. Yeah, whatever. And I guess I don't capitalize n, even though it's kind of constant. Queries, this length of queries, this number of rows, length of the first row. Wait, what am I doing? Think about this backwards. In range of, I guess it could be, yeah, I think that's right. I don't think I can do a multiplication of lists. I think it just doesn't work. I think I did that at some point. Actually, let me think about that. What if I did this times n increments of 0, append 0, print increments, return an empty list. Maybe that works actually. No. No, sir. I think that just multiplies the same reference. Okay. So this should be lists for underscore in range of n. This should work. 0 in the first list. Okay, so every query collapses the rows. Is that actually going to be fast enough? Yeah, might be still not fast enough, but it'll be faster. Okay, let's see. It shouldn't take very long to try to do this. Let's say R1, C1, R2, C2, oops, R2, C2 in query. So for each of those, I'm going to go, are these things 0 indexed? I think they are. Okay. For each row in range of R1 to R2 plus 1. So that actually includes R2. And then increments of the row and the tuple C1, C2. That's right. And then I probably want to sort increments for every row in range of n. Increments of the row is going to be the list. I'm going to sort that. So I have my tuples sorted. So I have, if I consider a list of the row tuples sorted by the lowest column, I make a stack to make a heap. I think I go through the tuples, considering their first index, which is the starting column index. I put maybe the second column in a heap, so that I always know what what the lowest exit column is, ending column. And then if I can pull out of the heap, that means I decrement the number of increments that is currently overlapping. So I think this should be something like, so for every row in ranged row, I guess I could probably just do it here. So I sorted the rows. Let's say my current is the current number of increments. Current valid incrementing range. Current number of valid increment. Current valid, current, maybe the active incrementing range of tuples. And then for every tuple here, so that would be start C, end C. I need a heap here. Yeah. N heap. We start C, end C in the tuples of this row, so increments of this row. And then I want to say, no, oops, no, I need to go actually, I need to have 2 pointers. I need a pointer, I want to have it, do I need 2 pointers? Actually, maybe I should just go through the starting indices and skip over anything that is, maybe I should go over the starting indices actually, yeah. So I need a current number of active indices, active tuples, and I need the current column. I think, no, it's not right, because I need to actually change the values in my matrix based on this. So I do need to go through every column is in a for loop. So for every column in range n. I think I need to go through. I think I need to index into the tuples of this row. Tuple index, maybe t-index. I think I can say while t-index is less than the length of the number of tuples in this row, and the current tuple has a start index that is equal to the current column. Yeah, so increments of this row, that tuple, the first value of it is equal to this column. Then I want to do t-index. No, I want to do end heap dot append increments row t-index the end column. This is a heap, and that's not how I push onto the heap queue. Heap push. Increment the current number of active tuples, increment the index. Yeah, and then that'll give me my current number of actives, which should be how much I put into the matrix at this position. And then I need to remove. So if the heap has the lowest active n column, then I need to take off any that matches this column. So while end heap and end heap of 0, the top of the heap, is equal to this column, and eq.heap pop it's the wrong syntax for heap push. Heap push needs to take in the name of the heap and the value to push. Value to push is the n column of the tuple. Okay, and then heap pop just takes the name of the heap. And each time I take out, then one less thing is active. I feel like I could possibly make a dummy something so that I don't have to check for existence of the heap. Like, so I could maybe make end heap have infinity, which is always going to be the biggest value in the heap, and then I don't ever have to check that the end heap is empty, because this will be just false when end heap of 0 equals infinity. Infinity doesn't go column. I guess that does make pushing into the heap a little slower. I wonder. Checking for existence versus always having an element in the heap. Actually, maybe that's actually faster if I don't have that dummy, because it actually does make it slower to push things onto a non-empty heap. below, see if I can make a dummy entry in the sorted row, then I don't have to check for the index going out of bounds somehow. So I could make just an infinity at the end here. And then index should never actually go out of bounds because it never increment past the end. That's fine. Okay. I think this is fine. Then I just return the matrix. Plural queries. Yep. Float is not scriptable. Interesting. Line 15. Increments at this row, at this index. Oh, it should be a tuple. Do. Okay. Should I just build some test cases that are kind of dummy test cases? Let's say there's no queries. Actually, can there be no queries? Queries is at least one query. Does it have to be correctly sized? Queries. Yeah, the queries are correct. Okay, so there's no like out of bounds query. It's gonna be a dummy one. I'll just do, let's say, a 5 by 5 and increment 4, 4 to 4, 4. Okay. Let's see my general test case mistakes. Or if it's too slow. Oh boy. That's kind of sad. It's really sad. Okay. Needs to be orders of magnitudes faster. Oh, that's orders of magnitudes faster. Less, yeah, 20 times speed increase necessary. So, huh. 20 times to do each query. So I think I think this is just the wrong or too slow of an approach. Incorrect in efficiency, time efficiency. What would make this faster? For each query, each query. I think this thing's going to be symmetric. It's not like it's going to be symmetric. Although it could be very similar row across row, like row 1 to row 2 could be very similar values. How slow am I doing this actually? Every column, every row, do the tuple thing, and then for each column in it, do the heap thing. Do I need a heap? I do need a heap. I do need to have a way to sort, because it could be something like it starts at column 0, ends at column 1, but then there could be some, or starts at column 0, ends at column 3. No, column 0 ends at column 2, starts at column 1, ends at column 1. Could in theory just create 2. Starts at column. Starts at columns. Wonder. Do I just need to know where the range starts and range ends? Have two separate lists for that? Not have a heap? Because it's not like I care about which ending tuple it is, it's just, as long as there's an ending tuple at the index. So I think I could make those, instead of a sorted list of tuples and a heap to track the ending columns, I could possibly just make it two sorted lists of starting indices and indices. I don't know that I am certain that that's just not fast enough, but I think it's a slight improvement. So I think it should be so let's say increments is the row append C1. It's when you increment the current active tuples. And let's say decrements is going to be also tracked. Decrements for this row append C2. Increment sort append I don't think this is correct anymore. I think it should probably still append infinity, maybe. Decrements of row sort decrements of this row append infinity. I'm not sure how you should be handling the out of bounds case here. And heap move. You do need to know the index into the increments. Yeah, you need to know index in increment index and decrement index. So while the increments for this row at the increment index is not a tuple anymore, is equal to this column, then current plus equals 1, the index plus equals 1, and then while I think I actually keep track of just the increment index, and I think I can take the difference between the two indices. To be the number of active ranges, and then here's just another while loop. While decrements for this row at the decrement index is equal to this column, decrement index plus equals 1. I think that's it. Oh, yeah, current. I don't need to keep track. Okay, I think that's fine. And see how much, if any, improvement there is. That's an order of magnitude. Slightly less than, or not order, it's like half the speed as before. Half the time as before. 4900, 1900, okay. Still not fast enough. Still the same kind of percentile within the overall distribution of solutions. What am I missing? What am I missing? 5, like, I guess currently my solution is something like n squared log n, maybe even n cubed log n. For each row, I'm sorting the elements in the row, so sorting the elements in the row would be n log n. And then I'm doing that for each row. So that'd be n squared log n. I think it's like n squared log n plus n squared, which is equivalent to n squared log n. So is there a way to do it in order of magnitude faster? 1, 1, 1, 1. I mean, you have to go through each element to assign the value to that element. So the question is, can you determine the value faster, I guess? It has to be some sort of nested for loop before for each row, for each column. I don't think you can shortcut that. For each row, for each column. I mean, there is something to be said about the fact that you could have very similar values in consecutive rows or adjacent rows in your sorted list. Like if it was just this one query, just would need to sort once maybe. What if you queries. So if you sort the overall queries, that sorts by the lowest row. Lowest row to highest row. But you really don't care about sorting by row because you're going to have to append it to the appropriate row anyways. So what if you sort the queries by column? If you sort the queries by the column in the column index 1, or the first column index within the query, if you sort it by that, then you're still going to go through the rows, but when you append when you append the column, then it would already be sorted. Yeah, it doesn't feel like this should be any faster. How do I do this again? P equals, like I would say this is lambda x, where x is a tuple there, where I want to use the 1, 2, no, or 1, 3, which is the column, first column index, second column index, row index, and I guess the other stuff doesn't matter. And then I think I don't need to sort here. Okay, let's see if that made any sort of difference. It's one less sort, one overall bigger sort. These are definitely just like minor improvements. But that was an improvement, like 600 milliseconds. I mean, it's an improvement on itself. It's not an improvement to the overall final solution. I guess that was actually a significantly decrease in time of my current solution. Alright, let's look at a hint. Imagine each row is a separate array. Instead of updating the whole submatrix, you can perform a prefix sum to update each row separate. Ooh. Spicy. Updating the whole submatrix and import prefix sum to update each row separately. We have a prefix sum. Yeah, I say spicy, but I don't actually know what they're talking about, to be honest. Because I don't think I used the prefix sum here, unless I'm mistaken. Prefix sum to update each row separately. Prefix of what? what I'm thinking was like maybe they were referring to creating some sort of kind of starting row and then modifying it. Modifying that row and do a copy that row and append that to the matrix. I mean, that might be faster. So you make like an initial matrix. You make an initial matrix. Or you make an initial row of values. And then you make an initial row of values. And then what? And then the queries will modify that row. The queries will modify that row. Yeah, I don't see how that's any faster. For each query, iterate over the rows in the range from row 1 to row 2. Add 1 to the prefix sum at I at that row in column 1 and subtract 1 from the prefix sum at that row in column 2 plus 1. Okay. And then for each, the value in the column is equal to, so it doesn't require any sorting, is that it? For each query, iterate over the rows. That seems like it's actually just the, it's using prefix, so it's not iterating over all the, it's not iterating over all of the elements of, I see, I think I see, so it doesn't actually sort. I guess sorting isn't necessary. I see, so skipping out the sorting. Okay, I think I might be able to do it with 2 hints. Okay, with just 2 hints. So it's very similar to what I have here, but without sorting. I guess the sort wasn't necessary. Yeah, so increments of the row and add a particular column. Add a particular column, which is C1 increment. Okay, so I do need, so this just stores this prefix sum, I see. So it's just collapsing in even further. So prefix 0 times n for every thing in the range n. This thing's not necessary. For every query, don't think I need these anymore. Prefix for this row at C1 is going to increment, and prefix at this row at C2 is going to decrement. C2 plus 1. Yeah. Which is really kind of the delta. So you have +1 there and -1 at the end. And you change the current by the prefix amount at this spot. Okay. So for every row in range n, let's say the current prefix is 0, or the current value is going to be 0. For every column in range n, the current plus equals the prefix at this row column. The matrix at this row column equals the current, and then just return the matrix. Out of bounds. This thing needs to be, yeah, just probably need to increase the size here, because it could, yeah. So this times the column length, so n+1. Oh, it's still not fast enough. Interesting. I guess I could definitely get rid of these things since they're no longer used. Current plus equals prefix. I guess I could use something like matrix at row column equals the prefix plus matrix at row column -1. Then I don't have the current variable. I don't know if that makes much of a difference. Probably not, to be honest. Equals matrix at row column -1 prefix at row column. Still too slow, I think. Yeah, that made no difference. Imagine each row. Instead of updating the whole submatrix together, from prefix sum to update each row separately. I think I did both hints as best I could. Convert each query into something of the prefix kind of matrix. That's without sorting. And then iterate and store values. Yes, I wonder if there's a way for me to skip over stuff that's like zeros. Skip over stuff that's like zeros. Probably not. If there was a way for me to detect when I had a bunch of empty space, I could maybe try to only go over the relevant stuff. Alright, let's look at the last hint here. After this operation for all the queries, update each row separately. S of ij equals S of ij plus S of j for all queries, update each row separately with prefix sum ij equals prefix sum ij plus prefix sum ij minus 1. That. Oh, I see what they're doing. They're saving space. They're using the same matrix for the return matrix as the prefix sum, and they're converting the prefix sum matrix into the return matrix. So prefix sum matrix at ij, so the matrix at row column equals the matrix at row column plus the prior same row prior column. I think that's what they're doing. Sij equals Sij. So the same row prior column. Update this. So let's say it was a single row. Let's say the row had 1, 0, 0, -1. Why would you update this thing to become 0? No, you don't. You update. You don't. Well, you ignore that this is going to wrap around. I think you update this to become 1, I guess. Yeah. And then you can update this and become 1, and you update this to become 0. Yeah. So they saved on having a prefix matrix and a return matrix. So that means for each row and range for the column, I think this should be column from 1 to n. And this should just be something like prefix of this row and column is equal to prefix of this row column. I guess this should be the value is equal to the value increases by whatever was prior. Prefix of row column minus 1. And at the very end I need to pop I think I need to pop a value off of this row. Prefix for this row pop, otherwise the sizing is incorrect. And then just return the matrix. I misspelled prefix. Did that wrong. For every column in range 1 to n, this should be collapsing. This should be the same thing as s of ij plus equals s of ij minus 1. Right, it should be, if it was going from this prefix, it should be the same value incremented by the prior value in the row, prior value in the row, prior value in the row. should be right. Okay, what's the actual? Oh. Wow, I returned the wrong matrix. Okay. Ah, please be fast enough. Really? So incrementally, oh, this is actually the same speed. So, okay, let's go and just remove some of this debris. Is there any way I can actually improve this, or based on the hints? I don't think the hints are actually greatly changing this. I guess maybe, okay, yeah, I can get rid of the matrix here. If I remember how to get rid of lines. It's not Control Z anymore. This still, yeah, this is still the same speed, I think. Even if I remove one matrix creation. Yeah. So there has to be some sort of dramatically faster way of doing this. For every row in range n, for every column in range 1 to n, do I have to go through the actual update each row separately with s of ij, update each row separately? S of 0, is there a way for me to skip? If the current spot is 0 and the previous spot is 0, skip? It's just additional check, so it's the same thing as actually assigning it, I think. For every row in range n, and sorting it just doesn't help because that's what I did originally. I guess I could store the first thing that's non-zero in the row and then work from there. Store the first thing that's non-zero in the row. And then only work in the bounded range. Wonder if that would work. Lows would be infinity times the number of rows. Highs would be infinity times the number of rows. And then I can say here lows for this row is equal to the min of lows for this row and the current column highs for the row equals max of highs for the row. Highs probably should be 0. Maybe C2 plus 1. Maybe. And then I can go for everything in range of lows for this row plus 1 up to highs for this row plus 1. Is it plus 1 or just highs for this row? Probably fine if it's plus 1. Float. I guess it could be n. I think that might be still wrong. It's made it worse, a lot worse back to prior to that. Yeah, that's a lot of checks. All right, this is one where I'm actually going to look at what the faster solution is. Oh, what? Classic code. Who needs descriptions when all you have? Who needs words when what you can do is just with letters and subscripts. So for everything in the query, so they create the same prefix thing. Okay, so this is not a nested query loop. Interesting. So it's for everything in row in the top left to the bottom, top left to the bottom right. No, this is just from the first row. Interesting. How'd they manage to do that? So it's like they're almost doing, they're skipping the intermediate rows, the in-between rows. How do they track that then? How do they track that? Row 2 plus 1, so they're going to the row below the ending row. And they're decrementing that. Okay. And they're going to the bottom right and incrementing that. Huh. Okay. Resulting matrix. The row index, the sum, for every column, increase, store into the matrix. If r is greater than 0, so as long as you're not on the first row, increase it by the previous row. Oh gosh. Oh, okay, so they're doing some sort of double prefix. Oh, I've never seen that before. Okay. Wonder if I can actually, based on just this one look, modify my code to kind of match the logic. So not only do you modify based on the the current row is a prefix sum, but also the prior row is a prefix sum. I think maybe. I guess the logic of the placement is a little weird. Okay, so I'll just, okay. I think it was something like the prefix stuff is 0 times n plus 1, but also for one more row. And then for every query, and the prefix is going to be the prefix at the starting spot increments. The ending spot, and I think they did the ending spot is, yeah, the ending spot is going to be past it, so C1 plus 1 decrements. I don't fully understand the logic why it's decrementing here rather than, well, I kind of understand it, but it's kind of intuitive. But what they definitely did was this is going to decrement as well, and then prefix at 1. Sorry, this is R2 plus 1. R2 plus 1, C2 plus, should be C2 plus 1. The first row, start index, end index is plus 1, C2 plus 1. That one increments. And then we have the return matrix. I think I could actually slightly improve that thing by popping stuff. Yeah, return matrix could be the same thing as the prefix matrix. So for every row in range n, for every column in range n, ooh, this is going to be interesting. Okay, so if you're not dealing with the first row, well, even if you are dealing with the first row, it's going to be something like prefix at row column plus equals, well, this should be 1 to n, I want to say. Is that right? Maybe it's not 1 to n. Because in the later rows, you still need to be put rows at column 0. I think this is, my gut feel is going to be row column minus 1. Modify it for everything here. Based on the prior thing on the same row. Before that, you need to change based on the prior thing on the first. You need to change it based on the prior thing in the previous row. I want to say this should be prefix of row column plus equals prefix of yeah, it should be 1 to n. of the row minus 1 column. Yeah. And then if the column is greater than 0, then do this. And I think that might be it. No, I need a pop. I need a pop. And prefix. Now it's a prefix at this row pop. And then prefix pop. So that removes the last row. Shucks. So this one works. So the first row is going to be fine. 1, 3, 3, 1, 2, 1. So, oh gosh. Yeah, that doesn't work, right? Doesn't work. Okay. Yeah, I do need to have separate matrices. Because, yeah, this just doesn't work for multiple, I don't think. Okay, so I'm going to say here, if the row is greater than 0, so I guess maybe I need to have a value. Value initially starts at 0 for every column. Maybe the value should be starting with the prefix at this row. Is that right? Did it modify both the prefix during the iteration here? No, it didn't modify the prefix. So the value, the starting value should be based on, what is the starting value based on? It's based on 0, based on incrementing by the current spot in the prefix matrix. And then if the row is bigger than 0, the result is modified by the prior column of that row. Okay, so increment space in the prefix matrix. Okay, I guess that makes sense. Pref s, the value increments by the prefix matrix of this row and column. And that stores into the matrix, the return matrix. Return matrix of this row column stores this value. And if the row is 0, then the resulting matrix increases by the prior row. Why would it always increase by the prior row? Prior row. No, wait, this is by the prior, yeah, this is by the prior row. I gotta simulate this to see why this works. Do-do-do-do. Okay. So let's go ahead and print out the prefix matrix here. One, -1. Okay, sure. So let's say this is the prefix matrix. So the value is 0, column. So I'm going through the rows and columns here. So row 0, column 0. 0 plus equals 1, so that's 1. So I store 1. So first row is, I'm not going to worry about the if statement. So the value increases by 0 next time, so 0 increases by 0 next time, so 0. Sorry. The value increases by 0. So sorry, the value should be now 1. So that stores 1. And then decreases by 1, so 0. And then 0 is n3 here. N is 3. One, 1, 0, okay. And then going to the second row, value starts at 0. Here, this starts at 0. And then it stores 0 initially. And whatever it stores, it increases by the prior row. So this is 1. And then it's at this spot, the value increases by 1, so it's now 2. No, the value is still 0. Yeah, okay. Increases by the prior thing, so the value is now 1, and then 1 plus 1 is 2. And then it goes to the third spot, I think that's 1. And then here it starts with values -1. So it stores -1, but then it increases that to 0. And then it's still a -1, but plus 2 is going to be 1. And now it's 1 plus 1 is 2. Value is now 1. No, the value is now 0. It's -1 plus 0 is 0. -1 plus 1 is 0. So now 0 plus 1 is 1. I guess I kind of understand that. Very interesting to see a 2D prefix array, prefix matrix. I have to do another problem with this in order to know when I fully understand, or to fully realize my depth of misunderstanding. For every value, I wonder if I could just do a slight change in syntax here. Value plus equals prefix at this spot. I mean, why can't I? The matrix changes by the prior row value. value matrix. Yeah, it's fine. Yeah. Okay. Summary. So this is complicated use of a prefix array / matrix to keep track of changes in the values within the matrix. Hard to summarize exactly what happened since I am still processing. Would suggest looking over the printout of prefix matrix and how that translates to the return matrix. Okay. This is going to be O of n squared, as there is a single pass over the queries to A over n squared plus q. To create the prefix array and a single pass over the elements of the matrix, which is n squared, to determine the n value of that spot in the return matrix. It's basic complexity of n squared for the prefix matrix, which has roughly the same dimensions as the return matrix. One more extra column and row in order to create the ending changes.